Thanks for watching this talk offline. After the FuzzCon, I got to know about the problems with the audio quality during the live recording. So together with the organizers at Code Intelligence, I decided to more or less record my talk again. And now with this hopefully stable microphone, which is now plugged above my head, it's kind of funny because in the live FastCon, you normally have a feeling that you have an audience who would then take some, who would ask you some questions. But now it's a strange feeling that I feel like I'm talking to a void here, where I cannot take any questions from live participants. But that's the way it is. So anyway, I want to sincerely thank my friends at Code Intelligence for inviting me to share our story. So before I begin, I want to tell you how this talk came to be what it is. So when I said yes to give a talk at FuzzCon this time, I was also curious to know about the audience, to get some statistics about what's the competence level with fuzzing of the participants who are attending this virtual conference. Then I came to know that some of you who were there, who attended, were pretty much new to it, who were taking baby steps into fuzzing, whereas most of you were experts and researchers who are championing fuzzing in your own domains. Seeing that, I felt that the most interesting aspect for this audience at FuzzCon would be to tell you the context within which we are applying fuzzing at Bosch Research. So I have put the title of my talk saying what's different about fuzzing automotive software. And for this, I have taken automotive software as the driving theme. You can, it's worth noting at this stage that automotive software is roughly also equivalent to embedded software or software which runs on IoT devices. And saying this, my talk assumes already a basic understanding of fuzzing. So in case if you are very new to fuzzing and you want to get some introductions, you can feel free to watch the other talks of FuzzCon before proceeding with this video. So now what's different actually about fuzzing automotive software? I've structured my talk along the following topics. I will start with the motivation to tell you why we are fuzzing automotive software, what are the different reasons to do that. And then I will move to the core topic of of this talk, where I'll tell you what's the difference when it comes to automotive software and how different it is when it is compared with web or IT-based software. Here, I will be telling you about some of the peculiarities which would make fuzzing quite a bit of a challenge to deal with. And after having talked about the differences, I would also give some ideas which me and my team are working on to cope with these differences. And finally, I will finish this talk with some conclusions for you. Okay, so to begin with, what's the motivation behind fuzzing automotive software? There are different motivations. So on the bottom left, on the bottom right of your screen, you see different levels of automation. So this levels of automation refers to the fact that as we proceed on automation level 3, 4, and 5, the amount of driving tasks which a car or an automobile would be doing would be significantly more than what a driver would be doing in this level 1 and 2 scenarios. So in this case, this already sets up a scene because the software has to be very robust, it has to be very reliant, and it has to be assured. So for higher assurance, one of the most proactive motivations for us is to continuously fuzz this kind of software which drives autonomous vehicles. So especially for level 3 and above, it is more or less, I would say, customary to kind of do these kind of fuzzing in-house and continuously as and when we build software. That's one of the motivation for us. And moving on, of late, the coverage guided fuzzing has picked up speeds, and it has also become very technically effective in this sense. So based on this, we also have scenarios like if we only do static analysis alone, we would end up with having too many false positives, and that's why we could then complement this with a kind of coverage guided fuzzing to kind of bring down these false positives and also find subtle bugs which go beyond simple coding guideline checks. So that's the second motivation for us to say that it makes sense to fuzz, and it also is technically effective, so why not fuzz it? So on this left left side, these two motivations are more or less inherent, intrinsic motivations, where one is of the belief that fuzzing makes sense and they just do it because either the software has to be highly assured or even that fuzzing makes sense in that case. On the right side, there could be other extrinsic factors or extrinsic motivations where there could be company internal guidelines or future norms which ask you to do fuzzing already during development. One such notable internal norm is that of Microsoft. They already heavily recommend that dynamic application security testing and fuzzing needs to be done as a part of secure software development lifecycle. So this could be an example of internal norm. And also if you look into future norms, which are pretty much in the shaping now, ISO, SAE 21434 and things like this, there could be a reasonable recommendation also from the norm side to say that fuzz testing and activities like this needs to be done. On the other side, there could also be customers requesting that fuzz testing be done. So these could be more or less like the manufacturers of cars who say these interfaces are pretty critical, so they need to be really tested for robustness, for security, for fuzzing and things like this. So there could also be requirements from the norm. So on the right side, you see the motivation being more or less extrinsic, where fuzzer gets kind of imposed on you. And trust me, and if you would have choice between the left two and the right two motivations, you would rather want to be more or less proactive and intrinsically do fuzzing than having to wait for future norms or even customer requirements to be imposed on you to do fuzzing. So all in all, there exists intrinsic and extrinsic motivation to fuzz automotive software. So where we stand now at this point is that we see a mix of both. In case of protocol fuzzing, there's already high awareness with customers where they say, okay, protocols need to be fuzz tested. But when it comes to software fuzzing, I would say it's more or less, the motivation is more or less intrinsic for us to be doing these kind of in-house fuzzing ourselves. So this finishes the first part. Now I would like to walk you through the core topic of my talk, where I'll be telling you about what on earth actually makes automotive software quite different and quite challenging to fuzz. So here I will walk you through 3 of the hand-picked differences. So I will just show you, I'll just start with the first one. This is the classic case when you see with embedded software that it is highly dependent on platform. So if highly portable software is what you know from most of IT or even web domains, welcome to the world of embedded software, where I would say that the software is so fine-tuned and so optimized that it only runs on a specific platform. And this is also for historic reasons. So that makes it particular because there is on one side a really strong platform dependence, and this comes from the fact that embedded devices are also resource constrained, so they need to be optimized, and that's why they have to be really tailored to one specific target platform. And it's also customary to see that the hardware in the loop testing is more or less always done because the tests have to be representative. They have to take timing into account and the target platform into account. That's why it's very common to see hardware in the loop testing. And also that due to safety norms, standards, most of the compilers which are being used are also qualified and even certified. So it's very normal to use certified compilers in automotive domain. So all of these peculiarities kind of create challenges when it comes to fuzzing, which are the impediments I'm talking about, because when we have software which depends on a platform and we have to take this software, kind of also build it and execute it without the hardware in the loop, then we have to be able to also stub the software and to eliminate this kind of platform dependency. So that's already the first challenge. And we see that the most coverage guided fuzzers, open source available ones like AFL++, libfuzzer, they really work harmoniously in a Unix or a Linux kind of environment. And to get automotive software compiled and executed on Linux is also quite a challenge that we see popping up now and then. And the other challenge which comes up when it comes to really big automotive projects is that the build chains are not so simplistic in that sense. We had a case where the build produced artifacts which were like code generated. They used to read configuration files and generate code based on them. And if we were to write a fuzz target on a code level, and we have such a complicated build chain, then the build chain used to override the fuzz target which we had handwritten in that sense, right? So there needs to be a even tighter integration with the build chain and the scripts, and in this case, and they require special treatment in that sense. And the last impediment comes to the also to the fact that what Silko earlier pointed in Fuzzing Sarikata, if you watched his talk on FuzzCon, he mentions also that the interfaces are not so trivial. So this is the same case with us, that the interfaces for automotive software are not that trivial, and this also creates quite amount of challenge in order when we want to actually create fuzz targets for them. So all of this peculiarities, I would say, doesn't make fuzzing so easy for us. So to sum up, we see that we face a high entry barrier to fuzz automotive software, and this is also because of the peculiarities, and which creates these challenges. And when I want to when I often mention high entry barrier, it's interesting to see also how other people kind of also approach this problem. If you have seen FuzzCon this time, Matthew Smith earlier in the morning touched upon the high skill requirement required for fuzzers for applying fuzzing in domains, because fuzzing can be the tools at the moment too expert friendly and not so developer friendly. So this also adds up to another dimension where I see that the need, first of all, there is a domain-wise entry barrier, as well as even the application-wise entry barrier when it comes to applying these tools and integrating them harmoniously with the build chain and things like this. So this is the first difference and the first challenge. Moving on, I would want to shift a bit of focus and talk about statefulness. So this peculiarity stems from the fact that automotive software is primarily stateful. That means that a set of state transitions have to happen even before something interesting occurs. So this creates challenges because traditional fuzzers, state-of-the-art fuzzers, they target software only with single input, and stateful programs, whereas on the other side require a sequence of inputs, and there is no adequate consideration at the moment for evolving program states during input generation. And it furthermore gets tricky when software runs in an infinite loop, which has to be appropriately reset to free up resource and things like this. So another challenge when it comes to trying out sequences is that the sequences that need to find a bug could be long, so that even the mutations could become infeasible. So all of them more or less sum up to this fact that we do require novel fuzzing techniques in order to fuzz stateful embedded software. So when I listened to FuzzCon this time, I was happy to hear from Marcel, who in the morning said that fuzzing cyber-physical systems, CPS, in that sense, is quite a bit of challenge, because these systems exhibit a different character that very much relates to what I'm talking about from the automotive side. And they also require adequate consideration when it comes to applying fuzzing. And exactly, so this is the second challenge when it comes to fuzzing embedded software, automotive software. So moving on to the third one and the last one, this difference these days is becoming more of a rule than an exception, because the software supply chain for automotive has become even bigger these days. And it is common to integrate third-party software, which are often available as binaries and where there's no access to source code. Such a setting makes fuzzing a bit tricky, especially when it comes to white box fuzzing, because white box is the one which is most efficient. And when you don't have access to source code, you lose some amount of efficiency when it comes to integrating these kind of software. And furthermore, if there are native binaries which are platform and hardware specific for a particular automotive project, these don't have emulation support when it comes to open source emulations like QEMU, Unicorn, and Gemfy. And this also creates quite a bit of an impediment to be able to fuzz these kind of software on these kind of native binaries in a scalable manner. So this challenge here is that we face the challenge of being able to find scalable approaches to be able to fuzz automotive binaries in a native manner. So the differences, the three of them which I mentioned, being platform dependent, statefulness, and integration of third-party binaries, I would say they're not so exclusive to automotive software, automotive domain alone. It is very likely that other domains like avionics or even others do exhibit similarities, but I picked them mainly from because these were more or less the predominant ones which we see in automotive. So moving on, I talked about the motivation for fuzzing until now and also told you how automotive software is different. And after having talked about the difference, now I want to draw your attention to how, what are the ideas and how is my team able to trying to cope with the differences and what are we innovating on. So the first one, if you remember, the challenge was high entry barrier. And here I want to give you a hint on how my team is trying to keep efforts manageable for various automotive projects. So if you look at a typical system under test or software under test, you can see fuzzers like AFL++, which provide inputs via standard and observe the behavior, crash or timeout or anomalies like this. So automotive software, as you've seen earlier, the input formats are not so trivial. So the trivial interfaces are not trivial, and they also require a special setup phase. And before even actually fuzzing, the fuzz target needs to be created. So because the fuzz target is so crucial here, because it is the connection between the fuzzer and the software under test, and the quality of this fuzz target directly affects the quality of fuzzing. And we've seen that most of the effort spent is because to connect the fuzzer to the and writing the to connect the fuzzer to the system under test, thereby writing the fuzz target. So to ease this effort, what we did is we came up with an abstract implementation, which more or less repeats or reflects the way in which a software is typically started up and input is fed and shut down. So the software developer who is working normally in their own context would know this information, and we have provided an abstract implementation where we hide the details of fuzzing, where the software developer only tells us what kind of how the software has to be started, what inputs it fetches, like they just write simple test cases, and we would then do the heavy lifting when it comes to fuzzing, where we add the build flags, the different configurations and sanitizers. And this way we try to keep the efforts reasonable on both sides. The assumption here is that my team which is handling fuzzing knows fuzzing in depth, and the software projects know the software development. So when these competencies kind of come together, we pool these competencies, then the efforts kind of also become manageable on the side. So this is one of the way to also lower the effort. And in this sense, we also try to find a balance between to kind of eliminate or not to separate the security specific activities from projects in order to kind of lower this barrier for security testing. This also relates to a bit of the earlier talk in FuzzCon, where Christian from Mozilla talked about a kickoff meeting, where I think the idea is similar to bring developers, fuzz experts, management all on the same table. So this is also exactly the same setting that we have seemed to have found independent of this, to keep the efforts kind of reasonable for us. So moving on, the second challenge was to come up with novel techniques to fuzz stateful software. So in order to do this, so we have come up with, we are still working, this is, as I said, ongoing research here. For the software developers, most of them are not fuzz experts. So for us, the motivation is to try to automate this process of finding interesting internal states as automatically as possible, so that the fuzzer can create mutations based on this. So if you see on the right side, a traditional fuzzing run happens in a way that a system under test is start up, then the fuzzer generates some inputs, forwards it to the system under test, and checks for crashes or anomalies. In stateful fuzzing, as we need more sequences of inputs, these need to be also created, rather just not just one input at a time, but a series of state transitions have to be supported. And that's what here is represented by this left green loop, where the traditional fuzzer is also kind of extended to kind of also support these the sequence of states. So the research arenas here for us include how do we identify a representative state, because automotive software often has very meager state machines, where if you send a state request, you would just get a yes or no response, rather than a lengthy verbose explanation what you would get from a web server. So these are all creates quite amount of challenges in identifying states. And then it comes to how do you build sequences? What are the heuristics that are required to insert, replace, delete the sequences, and rather than just doing it randomly. And finally, also it comes to the challenge of picking a state. It's like picking a corpus file, and how to select a global state to be fuzzed, and things like this. So this is, as I said, more or less the research which is ongoing at the moment, and where we do have a lot of open research questions. And I'm thankful these days that in the academic world, there's also more work in this direction. So an earlier paper called AFLNet already talks about, goes in this direction of fuzzing stateful implementations and also for network protocols. So I also see that this has a huge potential for further research also in the context of embedded systems, especially when it comes to stateful programs. So finally, the third challenge, if you remember, was to be able to fuzz native binaries. And this is a future work for us. The idea is pretty straightforward here. When a fuzzer on the left side creates inputs for the program, in the white box case, there is usually a chance to influence the compile time, add sanitizers, and then collect code coverage during runtime. All of this goes out of the window as soon as binary only is presented. So we need to find techniques also to reuse techniques available to inject sanitizers directly into the binary, because we cannot influence the compile phase anymore. And when it comes to runtime, because of also having emulators, which we need emulation techniques which support the execution of native automotive binaries. So this could be done in kind of a virtual hardware, which is something like a system C model, which basically takes the same binary and executes it. And due to the observability available within this virtual hardware, it is possible to collect runtime information and give it back to the fuzzer. So this is a technique which I think shows promise to us, because we would be able to then tap into this virtual emulation to then also fuzz automotive firmwares in a native manner. And going ahead here, we do see that we need more scalable approaches to be able to fuzz binaries, especially in automotive context. So yeah, until now, I've more or less covered motivation, what are the challenges, and how we are trying to cope with the differences. So I'm now gradually coming to the end of my talk. So to wrap up, I talked about the intrinsic and extrinsic motivations for fuzzing automotive software, and talked about the three handpicked differences. One is being the high entry barrier because of platform dependence. The second is the fuzzing of stateful, because embedded software is primarily stateful. The third is also fuzzing native binaries, which makes it quite complicated to fuzz. and how to cope with the differences by lowering the barrier through abstract implementations, pulling in the competencies, or also to be finding new novel techniques to fuzz stateful programs, and also new techniques to fuzz on virtual hardware, the native binaries. So having said this, fuzzing, I say, is definitely and also continues to be very important for automotive, and especially in this IoT software domain. In my team, we have already built such a platform, because fuzzing goes more than just having a tool. You need a framework around it, as you've seen from cluster fuzz, one fuzz, and things like this. So we have created a kind of an in-house platform to continuously fuzz Bosch software. So what we do is we take the techniques we use, make use of open source, pure vanilla AFL++, libfuzzer, and also goes beyond by adding grammar-based support, orchestrated fuzzing, stateful fuzzing, and things like this. So we apply to the Bosch software, which is primarily built on in-house. So in this sense, we have kind of built our own on-premise cluster fuzz, so to say. So if you are a researcher and wondering, and you have cool ideas to say, you want to, you have developed a tool or a fuzzing technique which also supports embedded software, then your new fuzzer can be just another bottle inside of our platform. So our platform is called Crate. You can imagine the Crate to be an extensible crate of bottles. And a lot of these bottles could even come from open source, could come from in-house, could come from even tool vendors, or even from researchers or from the academia. So in this sense, we have built an extensible platform which allows us to continuously fuzz software, but also to onboard the fuzzing which comes from the community. So if you're curious, you can feel free to get in touch with me. And just to mention one instance, so we do work closely with academia. In that sense, some of the PhD students of Professor Zeller, who gave a talk on taming fuzzers in the FuzzCon, is working with us as a visiting researcher at a campus in Renningen to put the fuzzer research to use on Bosch software projects. So before I end my talk, I would like to acknowledge a bunch of people. So during this automated security testing journey, I've had the privilege to work with really cool team, especially. So I have to thank my teammates, Simon, Christopher, Mark, Nishant, Anjali, and Rajat. So, and also last but not least, the management support for the topic has been really tremendous. So thanks also goes to Paul and Andreas for supporting us. And with this, I'm coming close to the end of my talk. So you see on the bottom left is the cool campus where we are working. On the right is my team, and we are indeed growing. So we do have open positions as of now, September 2020, for like research scientists as well as PhD. So if you are curious to apply and be a part of my team, so please feel free to apply over the job portal. With this, I end my talk, and thanks again for giving this opportunity to present the automotive side of fuzzing. And I hope you get back with questions or even offline with some research cooperations going further. Thank you. Take care. Bye-bye.